All right, let's dive right into the deep end of theoretical physics, shall we? We're going to explore one of its most fascinating, most mind-blowing ideas. The notion that our entire universe, everything we see and are, is actually shaped by a hidden geometry we can't even perceive.
So, you've probably heard this about string theory. It's one of our best shots at a theory of everything, but it comes with a pretty big catch. For the mathematics to hang together, it seems to demand a universe with 10 dimensions. That's 9 for space and 1 for time. But, when we look around, we obviously only see 3 spatial dimensions. So what gives? Where on earth are the other 6? To get to the bottom of that, we're going to follow the breadcrumbs. First, we'll see how it's even possible to hide dimensions. Then, we'll look at the super strict rules the physics imposes on them. That's going to lead us to a very, very special kind of shape. And then we get to the best part, how the geometry of that shape might literally create the laws of physics as we know them.
Okay, so first things first, how in the world do you hide 6 entire dimensions of reality?
Well, the idea physicists landed on is this really elegant concept called compactification. Think of it this way. Imagine a garden hose stretching across a huge field. From really far away, it just looks like a one-dimensional line, right? But as you get closer, you realize, oh, wait a second, it has a second dimension, a little circular part you can walk around. Compactification is basically that, but for the universe. The idea is that those extra 6 dimensions are curled up into a shape that is so incredibly, unbelievably tiny that for us, they're completely invisible.
But here's the thing. You can't just bunch up dimensions any way you want. That would be chaos. If you want to end up with a universe like ours, one that's stable and has the physics we observe, you have to play by some very, very strict rules. And this is where things get really specific.
The number one rule, the big one, is that this compactification process has to preserve something called supersymmetry. Now, the gist of supersymmetry is that every fundamental particle has a superpartner. To get a stable universe that doesn't just collapse on itself, the hidden shape must preserve just the right amount of this symmetry. Think of this as a powerful filter. It immediately throws out almost every possible shape you could imagine.
And this equation right here, this is the rule written in the language of mathematics. Now, don't worry, we're not going to solve it. But what it's saying, in plain English, is that the geometry of this hidden space needs to have this perfect, unbroken internal symmetry. It's like having a compass inside the shape that you can slide to any point, and it always points in the exact same direction relative to the space. It's an incredibly strict demand for balance.
So that one little equation forces the geometry to obey 2 really big conditions. First, the space can't have any kind of inherent twistiness to it. And second, it has to be Ricci flat. That sounds complicated, but it just means that even though the shape itself is all curved and complex, its overall curvature averages out to 0. It's the higher dimensional version of a perfectly flat sheet of paper. These are some seriously tough constraints.
So, with these tough rules in hand, physicists went searching for a 6-dimensional shape that could actually fit the bill. And believe it or not, a couple of mathematicians had already dreamt one up.
And this is where we meet the hero of our story, the Calabi-Yau manifold. These are a special family of shapes, first conjectured by Eugenio Calabi and later proven to exist by Xingtung Yau. And it turns out they are the absolute perfect candidates for hiding string theory's extra dimensions because they follow those supersymmetry rules to the letter.
So what makes them the perfect fit? Well, they have this very precise mathematical resume. They're complex and scalar, which gives them a really nice predictable structure. But the crucial parts, they are Ricci flat, check, that's exactly what we needed, and they have something called SU3 holonomy, which is just a fancy mathematical term for that perfectly balanced, unbroken internal compass we were talking about. They were practically tailor-made for the job.
And this beautiful diagram here, this is a Hodge diamond. You can think of it as a unique fingerprint for every single Calabi-Yau shape. It's basically a table of numbers that describes the shape's topology, like how many holes it has in different dimensions. But here's the kicker. As we're about to see, these numbers are so much more than just abstract math.
All right, get ready, because this is the most amazing part of the whole story. This is where all of that abstract geometry gets real and turns into the actual physics of our universe.
So in string theory, all the different particles and forces we see are just different vibrations of a tiny string. But get this, the shape of the Calabi-Yau manifold, the little space where the strings are vibrating, determines how they can vibrate. The geometry literally dictates the physics that we experience out here in our 4-dimensional world. It's incredible. And this right here is the magic dictionary. This is how we translate the geometry into physics. Remember those Hodge numbers from the fingerprint? Well, the number called H11, that tells you how many different types of certain particles you're going to get. The number H21 tells you how many of another kind. And most amazingly, you combine them in a certain way to get the Euler number, and that tells you the net number of generations of matter, like the electron and its heavier cousins. The number of holes in this shape tells you the number of particles in the universe. It's just wild.
So if we actually go through with this, if we pick a specific Calabi-Yau manifold and build a universe on it, what do we get? What kinds of particles actually pop out of the theory?
Well, the theory predicts a whole slate of particles. First and foremost, you get gravity, which is huge. You get the force-carrying particles, the gauge bosons, and you get the matter particles that make up, well, everything. But look closely. The number of different kinds of matter is determined directly by those Hodge numbers, H21 and H11. The physics is literally just a printout of the geometry.
And this is the ultimate prize. This is the whole point of the exercise. We know that in our universe, we have 3 generations of matter. So the hunt is on to find a Calabi-Yau manifold whose Hodge numbers spit out the number 3, along with all the other particles and forces we see in the standard model. The entire blueprint for our reality could be written in the very fabric of one of these hidden shapes.
And hey, don't just take my word for it. The source material spells it out. The low energy effective action, that's just physicists speak for the laws of physics in our everyday world, is determined by the topology of the Calabi-Yau manifold. It doesn't get much clearer than that. The link is direct.
So that leaves us with this absolutely profound question. Is it possible that everything we see, from the tiniest particles to the grandest forces that hold the cosmos together, is nothing more than a reflection of the twists, the turns, and the holes in a tiny, 6-dimensional shape, forever hidden just beyond the reach of our senses? Could the deepest secrets of our cosmos really just be geometry? It is a truly stunning thought.